Our next example of computing an expected value is a lottery game again, and this time you pay 50 cents for your ticket and you choose a 3-digit number. The lottery picks a 3-digit number randomly and pays you $250 if your number matches. First, we're going to write down the probability model for your gain. This is what you'd write if you were using way 1, the outcome probability table. So we're going to write outcome probability. And we want to do it for the gain, not the winnings. So what are the two possible outcomes? You either win or you don't win. So if you win, how much do you gain? Well, you spent 50 cents, but you'd win 250, so you'd gain $249.50. And if you don't win, what's your gain? You just lose the money that you spent on the ticket, which is 50 cents. So minus 0.5. Now, what's the probability that you win? Well, picking a 3-digit number randomly, how many 3-digit combinations are there? There's 001 all the way up through 999, which is 999 possible combinations, but don't forget about 000. That makes 1,000 possible 3-digit combinations. So the probability of a 3-digit number being randomly picked is 1 out of 1,000. And then, since the only other possibility is to not win, that would be the other 999 out of 1,000 times, because remember, your probabilities have to add to 1. So now we've got our outcome probability table written. So if we choose to compute this with way 1 according to the definition that's given in your book, then your expected gain is $249.50 times the probability sitting under it, which is 1 out of 1,000, plus the next outcome times its probability, which is negative 50 cents, times 999 over 1,000, because that's the probability sitting under that outcome. And now we've exhausted all the outcomes and probabilities, so we're done except for computation, and when you punch this in your calculator, you should get minus a quarter. So on average, if you were to play this game many, many times, you can expect to come out losing a quarter on average. Or way 2, to compute expected gain, is to take the amount you could win. We've only got one amount we could win here, so that's $250, times the probability of being the person that wins, 1 out of 1,000, and then subtract the amount that you spent on your ticket. And if you punch that in your calculator, it again comes out to be minus 25 cents. Now, expected value is how a casino is a business. It's also how your insurance company is a business. So let's think about a very oversimplified insurance policy and the expected gain. An insurance company sells a particular policy that costs the insured $1,000 to purchase. The insurance company knows that 1 out of 100 of these policyholders will file a claim worth $20,000. 1 out of 200 will file a claim for $50,000, and 1 out of 500 will file a claim for $100,000. Find the insurance company's expected gain for this policy. So if we're looking at the gain for the insurance company, if they're a good business, then we should be getting a positive number at the end. So that's what we're expecting to get here. All right, so we're going to write our outcome probability table first. All right. Now, for the insurance company, what is one possible outcome that's going to happen? Well, you could file the $20,000 claim. So that means that they would gain negative $19,000 because they took your $1,000 and then they had to pay you $20,000. So they're out in the hole $19,000. And how often does that happen? 1 out of 100 times. That was given in the question. All right, what's another possible outcome for them? Well, you could file a $50,000 claim, but remember they're only really losing $49,000 because they took your $1,000. So they could be in the hole by $49,000 if they paid that claim. And that happens 1 out of 200 times. What's another possible outcome? They could pay the $100,000 payout, and that means they would be in the hole by $99,000. And that happens 1 out of 500 times. And what's the last outcome for them? If they don't pay out any claims. In that case, they come out ahead $1,000 for the people that don't turn in a claim. So, in that case, we need to find the probability of them not paying a claim. Now remember, these probabilities all have to add to 1. We could either take the time and get a common denominator for our fractions, or we could just change our fractions into a decimal. And I found over the years that most of my students like to punch things in the calculator and turn their fractions into a decimal, so that's the way I'll do this. I'm going to put 1 divided by 100 in my calculator, plus 1 divided by 200, plus 1 divided by 500, and I get 0.017. So 1 over 100 plus 1 over 200 plus 1 over 500 is 0.017. And so what does this amount have to be? It has to be the number that makes all 4 of these categories add to 1. If the other 3 categories add to 0.017, I can just take 1 minus 0.017 to get that probability. So 1 minus 0.017 is 0.983. All right. So make sure you practice that so you're capable of doing it when it comes time to do it on your own. So now we have our outcome probability table, and we want to compute the expected gain. So we're going to do way 1 first. Once we have our outcome probability table, we can just rock and roll through our formula. So the expected gain is going to be the first outcome times its probability, so negative 19,000 times 1 over 100, plus negative 49,000 times its probability, which is 1 over 200, plus negative 99,000 times its probability, which is 1 over 500, plus 1,000 times its probability, which we put in decimal form, 0.983. And if you punch that in your calculator correctly, you're going to get $350. So on average, the insurance company keeps $350 per policy. That's the way we interpret our expected value. In the long run, for each policy they sell, they can expect to make $350. Now we'll compute this using way 2. Way 2, remember, uses the original amounts and then subtracts the amount that was spent on a ticket. In this case, we'll add the amount that a policyholder pays for their premium. So way 2 would look like this. Expected gain is the first loss they could pay, which is minus 20,000 with its probability times 1 over 100, plus losing 50,000 times its probability 1 over 200, good grief, plus losing the 100,000 with its probability, 1 over 500, and then plus the amount of the purchase of the policy, which is 1,000. And if you punch that in your calculator, again, you're going to come out with $350. So like I said, a lot of students compute these both ways just to be sure that they have some measure of comfort that they have gotten the correct answer. Now, Chapter 20 accentuates the law of large numbers again. So notice that the expected value of a variable is a weighted average of all the possible outcomes. It represents the long-run average and we will actually see if we observe the random phenomenon many times. It makes sense intuitively to believe that the more trials we observe, the closer our observed average should be to the true average. This can be proved mathematically, and that's the law of large numbers. So once again, if a random phenomenon with numerical outcomes is repeated many times independently, the mean of the observed outcomes approaches the expected value. And remember that expected value is another word for population mean. Those are interchangeable terms, and sometimes it makes more sense in speaking and in layman terms and in our interpretations to use the word expected value rather than population mean. Population mean sounds a little less tangible. And what's the mean of the observed outcomes? That's your sample mean. So what the law of large numbers is saying is that as your sample size gets really big, your sample mean should start to look like your population mean. The law of large numbers is closely related to the idea of probability. In many independent repetitions of a random outcome, the proportion of times a random outcome occurs approaches the probability of that random outcome. And the average outcome obtained will approach the expected value as you increase the number of observations. The law of large numbers explains why gambling is a business for a casino. And one last note, the more variable a random outcome is, the more trials are necessary for the mean of the observations to be close to the expected value. Think about playing the lottery. If you could win $5 million, but it's a 1 in a billion chance, most people are going to win $0. So if you average 1,000 people's winnings, you're probably just going to still see an average winnings of $0. That's a really variable outcome. 0 versus $5 million. There's a lot of variation in the possible outcomes. And so we need to see a lot more trials in order for us to see the sample mean start to look like the population mean.